Hey everybody, welcome to the guided assignment for chapter 5. I'm just going to walk us through it like we always do on guided assignments, and hopefully it will make it a whole lot clearer. So this chapter is on discrete probability distributions. And remember, discrete just means our values within these probability distributions only take on the values of whole numbers, no decimals or in between places. Now, that's the value of the variables, but our probabilities that we'll be calculating will definitely have decimals in them. So it's just the numbers in the data set will always be whole numbers. That's how we can tell discrete, and often it will tell us. And so we're going to work with the three types of discrete probability distributions in this chapter. All right, so let's take a look at the first one. It says 3 students scheduled interviews for summer employment at Brookwood Institute. In each case, the interview results in either an offer for a position or no offer. Experimental outcomes are defined in terms of the results of the 3 interviews. So first it says list the experimental outcomes. So we can either have 3 no's, 2 no's and a yes, a no, yes, no, a yes, no, no, a no, yes, yes, a yes, no, yes, a yes, yes, no, or a yes, yes, yes. Those are all of the possible outcomes of this distribution. And then it says, let X equal the number of students who receive an offer. Is X continuous or discrete? And the answer is, it is discrete. And why is it discrete? Because it's only whole numbers, right? Only we can have 0, 1, 2, or 3 people receive job offers. So if X is the number of people who receive it, then it's discrete. Those have no decimals, just 0, 1, 2, or 3. All right. Now it wants us to show the value of the random variable X for each of the experimental outcomes, where X is the number of yeses. And a yes means they receive an offer. A no means they do not receive an offer. And then it says if our answer is 0, meaning that nobody receives an offer in the data set, we'll put 0. Or if our outcome does not, if the experimental outcome does not occur, enter 0. So like these first few, they can't happen, right? Because there were 3 interviewees. We could have a yes, yes, no, but we can't just have a yes, yes. So because there has to be 3 results, we're going to put 0 for these because they're not real outcomes of 3 interviews. And then on all the others, we're just going to count the number of Y's, the number of yeses, and that will be the value of X. So there's 2 on that one, 2 on that one, 1, 1, 3, 0, 1, and 2. Check our work, and voila, all green checks. So we feel pretty good about that. So we will move on to the second problem or second question on the guided assignment. All right, so here we have a technician services mailing machines at companies in the Phoenix area. Depending on the type of malfunction, the service call can take 1, 2, 3, or 4 hours. The different types of malfunctions occur at the same frequency. If required, round your answers to 2 decimal places. So it says develop a probability distribution for the duration of a service call. So the hint on this one is that the types of malfunctions occur at the same frequency. Okay, so that means there's an equal chance of any one of these happening. And so really all we have to do is if 100% of the time it is either 1, 2, 3, or 4, and we only have 4 options and they break down to being equal or having the same frequency, we'll just take 100%, divide it by 4, and say there's a 25% chance of it being a 1-hour call, a 25% chance of it being a 2-hour call, 25% of it being a 3-hour call, and all of those will add up to 1 or 100%. So that's how we kind of deal with that, is to say it's when it says that they occur at the same frequency, that makes our life pretty easy because we know then it'll be the same number or the same probability or frequency of any of those. All right, and then it asks us which of the following probability distribution graphs accurately presents this data set. And so again, we would be looking for something where they're equal all the way across. So that would exclude 3. and then it would be something between 20 and 30, right? So those are 25% each, so it's going to be number 2. All right, C asks us consider the required conditions for discrete probability shown below. So 1 is that each item, the f of x of each item is greater than or equal to 0. So each of these can be 0 or greater, but it can't be less than 0. So I guess the question is, does it meet the distribution, or does the probability distribution satisfy equation 5.1? Yes, each of our f of x, each of our items is greater than 0, greater than or equal to 0. So we'll say yes. And then the second one is that the sum of the functions have to add up to 1. And indeed they do. So we're going to say yes, the sum of all the probability functions equals 1. And that's because if we know all of the possible things that can happen, then the probability of each of those happening has to add up to 100%, right? Something's going to happen. We just don't know exactly which. In this case, we know that when we go to make a visit, it's going to be 1 hour, 2 hours, 3 hours, or 4 hours. So the probability that it is 1, 2, 3, or 4 hours adds up to 100%. All right. What is the probability a service call will take 3 hours? So again, we can look at this and say, well, that probability is 25%, 0.25. And finally, the last one says a service call has just come in, but the type of malfunction is unknown. It is 3 p.m. and our service technician usually get off at 5 p.m. What is the probability the service technician will have to work overtime to fix the machine today? So if it's a 1 hour job, they'll finish by 4. If it's a 2 hour job, they'll finish by 5. If it's a 3 hour job or a 4 hour job, they'll have to work overtime to get it done today. So we would just add these up. We would say, well, there's a 0.25%, or a 0.25 or a 25% chance it will take 3 hours, and a 25% chance it will take 4 hours. So together, that's 0.5. So what we're saying is there's a 50% chance the technician will have to work overtime to get the job done today. Let's double check. Those all look good. We can move on to number 3. All right. So number 3 here says the following table provides a probability distribution for the random variable y. So I'm just going to go ahead over here in Excel. See if I can get that up a little. I don't want it to do the whole page, but I do want to have it high enough up that I can adjust its being done. Okay, I'm just going to do it now. I'm going to adjust this a little bigger. And then I'll put it back to half screen. There we go. All right, so we have y and the function of y. And our y values are 2, 4, 7, and 8. And our function of y, which is the probability of those, is 0.2, 0.3, 0.4, and 0.1. All right. So the first thing it asks us to do is to compute the expected value of y, okay, or the e of y. And so, sorry, I like to have them centered. So the expected value of y, whoops, is really just another way of saying the average. If we look in the book, it'll give us a formula, a mathematical formula. I'm going to show you how to do it on Excel. So to find the expected value of y, we're just going to multiply y times the function of y for each of these. I'll fill down. And then we'll take the sum. And that number right there is the expected value of y. If you think about it, it's just an average of each of these. And so if we have, if the probability that it's 2 is 20% and 4 is 30% and 7 is 4% and 8 is 1%, then the probability, or then our average value is going to be somewhere between 3 and 4, and it's 5.2. So the formula will just say that the e of y, which is the expected value of y, is the sum of y times the function of y. Okay, that's what the the formula says. So we're going to put in 5.2. And now it wants us to compute the variance of y and the standard deviation. So this little symbol right here, which is a Greek letter sigma, it means standard deviation. So the formula for the standard deviation is that we're going to take our value of y minus the expected value of y. So this is what, whoops, y minus EY. Then we're going to square that. Okay, so it's going to be y minus EY squared. Oh, but you know what? I have to be careful. I screwed up right here. So when I did y minus the expected value of y, but then when I drug this down, check it out. Now it did this number of y minus this, which is 0, right? So I have to be careful whenever I'm going to be filling down like that. I need to lock it in on this cell, because so what I'm going to do to lock it in is I'm going to put a $ in front of that D and after that D. And now that will tell Excel, hey, when I use the fill tool and fill down, you can still move and shift the value of y, but stay locked on this cell. And so now you can see it's 4 minus 5.2, 7 minus 5.2, etc. So that's what putting those $ does. It locks it in on that one cell. All right, so now to square it, I'm just going to say this equals this number, which is y minus the expected value of y. We use this little shift and the 6 key, which is a to tell an exponent, and then put 2. So we're going to square that number. And now we take the value of f of y, so the probability, times the value of y minus the expected value of y squared. And now the sum of all of these values will be our variance. Again, there's a formula in there you can check out. But really just remember variance is sort of how widely dispersed the data set is. And so what we do is we take each value of y and subtract it from the mean or the expected value. Then we square it to get all those negative numbers out of there. And then we multiply that times the probability of any one of those happening, and that'll give us our variance. And then our standard deviation is always just the square root of the variance. And that's because since we squared it here, we end up in squared units. So to have it be something more meaningful, we take the square root, and that gives us back into our single units of whatever y was, which we actually don't know for this problem. And there is our standard deviation. So that's the variance, and that's the standard deviation, 2.14. Check our work, make sure I didn't make an error somewhere, but I didn't this time, so I got lucky. All right, let's move on to number 4. All right, according to a 2018 survey by bankrate.com, 20% of adults in the United States have nothing for save nothing for retirement. Suppose that 15 adults in the United States are selected randomly. Okay, so we're going to go through this part first. The selection blank is a binomial experiment because adults are selected randomly. Okay. And the probability does not change from trial to trial. It's 20%. Each time we pick somebody, there's a 20% chance that they don't save anything and an 80% chance that they do save something. Okay. The trials are independent. and there are exactly two outcomes possible. Either they save or they don't save. Okay, so those are the, I guess, the rules for something being a binomial experiment. All right, so that's all right. So now it's going to ask us, what is the probability that all of the selected adults save nothing for retirement? So I'm going to show you something real quick. So in Excel, let me just delete this. In Excel, if we put in the function equals binom.dist, it will give us what it calls the arguments, or the information it's going to need to calculate the probability of a binomial distribution. In this case, it's number underscore s, which means the number of successes, and then trials, which is the number of um, let's see, the number that we select. Okay, so it'd be like n, the number of trials, and then the probability of success, and then cumulative. And cumulative, for these discrete variables, it just means, are we trying to figure out if it's exactly a number? Like, and I'll explain it as we go through it, or if it's that number or fewer. Okay, so that's what we're going to need. So I'm just going to actually set up my problem that way. I'm going to say number of successes, trials, and probability are the three pieces of information I'm going to need. So number of successes, what did I just say? Number of successes. I better look at it again. See, that's the great thing. If you forget somehow, just look. Trials and probability of successes. And then the probability of success. All right, so let's take a look at what that means. So it says, what are the probability that all of the selected adults are saving nothing for retirement? What's confusing about this term of success is most of us wouldn't think it was a successful thing for adults to save nothing for retirement. But we have to define our successes. So this tells us that according to our survey, that 20% of adults save nothing. So we're going to say saving nothing is what we call a success for this problem. So what is the probability that all of the adults save nothing? So that would mean that we would have 15 successes out of 15 trials, because we selected 15 people randomly. And so if all 15, sorry, those numbers are bugging me. If all 15 do not save, then that would be a success, okay? And then the probability of success for any given one item is 0.2, okay? So that's how we set this problem up. So now we're going to say, well, the probability, so in this case, the probability that we ask or select 15 people and none of them are saving anything for retirement is binom.dist, where we have number of successes, 15, number of trials, 15, the probability of success on one trial, 0.2, and then cumulative, which means either that we're going to, if we say true, let's just look at it. If we say true, then what we're saying is, what's the probability that it is 15 or fewer successes? So whenever we put true, we're saying, what's the probability of this number of successes or fewer? So you think about it, if I'm saying 15 out of 15 trials, what's the probability that I hit 15 or 14 or 13 or 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, or 0? Of course, the probability will be 1. So remember, true equals that amount or fewer, okay? So that's not going to work for our problem here. So instead, I'm going to say false. And when I say false, I come out with this incredibly tiny number, right? So if I put this in terms of that, and it says, so go to 4 decimals, it's going to be 0. So the probability that if it's 20% success rate, and the probability that I'm going to get 15 out of 15 as successes, which in this case, a success means that they don't save, then I'm going to say that probability of that occurring is 0. It just isn't going to happen, okay? So the second one says, what's the probability that it is exactly 5 of the selected adults save nothing? So now I'm going to say 5 successes out of 15 trials, where the probability of success is 0.2. Remember, I said false, so false means exactly 5, and that's what it asked me for, exactly 5. So my probability is going to be 0.1032, or about a 10.3% chance that out of asking 15 people, 5 people will say they don't save anything. And now this last one's a little bit confusing because it says, what's the probability that at least one of the selected adults save nothing for retirement? So at least one means 1, 2, 3, 4, 5, all the way up to 15. The only thing that wouldn't fit in that is 0. So unfortunately, with the binom.dist function, okay, we can't do a certain number or greater. So instead, what we can do is we can say number of successes is 0, and we can say 0 or fewer, which will actually come out to the same because you can't have fewer than 0. So now this gives us the probability that it is 0 or fewer, okay? So the probability that it is greater than that is going to equal 1 minus the probability that it is 0 or fewer. So this gives us the probability that at least one person, 1, 2, 3, 4, 5, up through 15, don't save anything. So there's a 96.48% chance that at least one person saves nothing for retirement, is what this really turns out to be. Just remember that all of the probabilities in the total function have to add up to 1. So if I can calculate the probability that something is less than 1, which means 0 or less, then I go 1 minus that will tell me the probability that it is 1 or greater. So I'm going to put 0.9648. Check my work. Hopefully I'm all good. And I am. All right. So let's move on to the Poisson probability distribution. If you want to say it really Frenchy, you can, like Poisson. Just don't say Poisson, because that means fish. And I don't think it's a fish distribution. I think it's a guy's name. So some French guy, right? So this tells us airline passengers arrive randomly and independently at a passenger screening facility at a major international airport. The mean arrival rate is 10 passengers per minute. So I know this is a Poisson probability distribution because we use these distributions for measuring rate, like the number of passengers per minute or cars that pass a place per hour or whatever that is. So look for that relationship when you're not sure if it's about the number of things happening per amount of time. That's how you're going to identify it as using the Poisson distribution. It's an important part of this chapter and the next to identify what type of distribution you have first, and then to kind of launch into the math of it, okay? So let's take a look at it. So again, if we want to kind of see the arguments of a Poisson distribution, Poisson.dist, and we need X, and we need a mean, and then we need cumulative, true or false. So that's all we need. So we'll set up our problem with a value of X and a mean, and then we'll type in true or false. All right, when it comes to that. So airline passengers arrive, the mean arrival rate is 10 passengers per minute. And I'm just going to put over here a little note, per minute, okay? So the first question says, what is compute the probability that there are no arrivals in a 1 minute period? So X would be 0 if there's no arrivals. So I'm going to say probability equals Poisson dot dist, where x is 0, the mean is 10, and then we're going to say that this is this says no people arrive, so I'm going to say false, exactly 0. And I get this number 0.454 exponent means times 10 to the negative 5. But this one wants my answer to 6 decimals. So I'm going to go ahead and, well, okay, I'm going to tell it, if I click on this comma, that means just give me regular numbers and I'll take it out to 6. 1, 2, 3, 4, 5, 6. Yeah, so it's 0.000045. That's the probability in this case. So the next one says, compute the probability that 3 or fewer passengers arrive in a 1 minute period. Okay. So I'm going to put probability fewer. Okay. So here I'm going to say 3 passengers in the 10-minute period. I'm sorry, in the 1 minute period where we have 10 as our average. So here would be the probability of exactly 3, but we want the probability of 3 or fewer. So we're going to equals binom dot dist. And then I'm going to put 3, number of successes. Oh, not binom. Sorry, guys. This is a Poisson. Poisson dot dist, where 3 is my x. My mean is 10. And in this case, it's true because that's going to give me the probability of 3 or fewer. So that comes out to 0.0103. So only about a little better than a 1% chance of 3 or fewer people coming through in a minute. All right, so C and D can get a little confusing because remember, this mean we're given up here is a 10 per minute, but this one says compute the probability of no arrivals in a 15-second period. So they trick us here because this is 10 per minute, and we're going to have to reset our mean to a 15-second interval. So if there's 60 seconds in a minute, then there are 4 15-second periods in a minute. So all I'm going to do is take this number 10 and divide it by 4. And that's going to give me my mean per 15-second period. Okay, so if we average 10 per minute, then we're going to average 2.5 per 15-second period. Okay, so now it says compute the probability of no arrivals in a 15-second period. So again, I can go back to 0. And the probability that it is exactly 0 is, it wants 1 decimal. And here you'll see they're the exact same, and that's because the probability of exactly 0 or 0 or fewer is the same because you can't get fewer than 0. But it's 0.0821. And the probability of at least 1 arrival in a 15-second period. So remember, at least 1 is going to be 1 or greater. So the probability that it is greater is just going to be 1 minus the probability of it being 0, right? Because anything greater than 0, 1 up through whatever, is what we're looking for here, 1 or greater. So it's going to be 0.9179. Check our work. Hopefully we'll get all green check marks, and we did. And only 1 more to go. I bet you're happy about that. I'm always happy when I'm down to the last one. All right. So number 6 is a hypergeometric probability distribution. That's a scary sounding name. Don't worry, we have a function for that. So this one's about blackjack, the card game. Is a popular gambling game played in casinos. The player is dealt 2 cards, face cards, jacks, queens, and kings, and 10s all have a point value of 10, and aces have a point value of 1 or 11. A 52-card deck contains 16 cards with a point value of 10 and 4 aces. And then it wants what's the probability that both cards dealt are 10-point cards, the probability, etc. So we're going to use a hypergeometric distribution. And the reason it's a hypergeometric distribution is our probability changes each time we draw out a card, right? We had 52 cards to start, but once I pull my first card, now I've only got 51 for when I make the second draw, okay? So take a look at the arguments. It's hype geom.dist. Whoops. Equals. I think I did it right. All right, so the arguments for this one are a little more complicated. We have sample successes and the number in the sample, population successes and the number in the population, and then finally cumulative, okay? So that's the arguments that we're gonna set up our problem here. So I'm gonna do sample successes and number in the sample and population successes and the number in the population, and then finally the cumulative thing, okay? All right, so let's talk about what each of these mean as we go through the problem. So the first question is, what is the probability that both cards dealt are aces or 10-point cards? And remember, we have 16 10-point cards and 4 aces. So we would say the number of successes, we're drawing 2 cards. And so if the probability that they're either 10-point cards or aces, we're saying we want 2 samples or 2 successes out of a sample of 2. As we're drawing 2 cards and we want both of those cards to be successes. And right now we're defining successes as any card that's a 10 or an ace. So the population, or the number of cards that are a success in the population, are the 16 10s plus the 4 aces, or 20. So there's 20 potential successes in the population. And then the number of cards in the total population is 52. Whoa, that one's still got all the decimals set up on it. All right, so there's the setup for our problem. Sample successes and the number in the sample. Number in the sample is like the number of cards you're drawing. And how many do we want to be a success out of those 2? Both of them. And there's 52 total cards to draw from, and 20 of those 52 would equal a success by being either a 10-point card or an ace. All right, so we're ready now. We're going to say probability. And we're going to say equals type geom.dist sample successes, comma, number in the sample, comma, population successes, comma, number in the population, and then we're going to say comma, false. So what's the probability I get exactly 2 successes out of 2 draws when there are 20 successes potentially out of 52 total? And the answer is 0.1433. So about a 14.33% chance of drawing 2 cards that are either 10-point or aces. Now it says, what is the probability that both of the cards are aces? So here we still have two samples drawing 2 cards and 2 successes, but our population successes drop from 20 down to 4. There's only 4 aces in the whole deck. So you can see that number gets a lot smaller. That probability is 0.0045. So slightly less than half of 1%. What is the probability that both of the cards have a point value of 10? So now we're going to say, well, how many 10-point cards are there? 16. So our population successes would be 16. So 0.0905. So you have a little better than a 9% chance of drawing 2 10-point cards. All right, so the last question is an interesting one, because it says a blackjack is a 10-point card and an ace. Use your answers in part A and B determine the probability that a player is dealt a blackjack. And then it gives you a hint that it's not a hypergeometric problem, so develop your own logical relationship. So here's what I want you to think about. There's a 14 or a 0.1433 chance that they're either aces or 10-point cards, okay? There's also a 0.0045 chance that they're both aces and a 0.0905 chance that they're both tens. So I want you to think of like all of the possibilities involved here in the one that's 14 or 0.1433. That could be two aces, two tens, or an ace and a 10. So if I take this probability, I'm going to just say 10 or ace, 0.1433. And then I say both aces, 0.0045, and both tens is 0.0905. The only other option I'm left with is one ace and one 10. So the total of both aces plus both tens plus one ace and one 10 must add up to the total of drawing tens or aces. Okay, so I'm just going to say this is the probability that it is 10 or ace minus the probability that they're both aces minus the probability that they're both tens gives me the probability of getting a blackjack, which is slightly better than almost 5%. So slightly better than 4%, actually 4.8%. So 0.483. Let's check our work. And hopefully, oh, it's 0.0483. That was my bad. Don't forget your leading zero there. Let's check our work. And now we're good. All right. I hope that was helpful to you. I know it was a little bit long, but I'd rather explain it well and have it take a little while, and then you'll be in a better situation when you get into the homework. Have a great week. And if you have questions, don't be afraid to ask.